Okay, this is new thermodynamics and continue with unraveling Gordian knot just because to me it's a big mess, okay? And we're going to talk about inelastic versus elastic collisions and other absurdities with the implications. Okay. Traditional thermodynamics is founded upon certain principles, one being elastic collisions. And really what this does is this limits all the system's energy to its kinematic energy, that being the energy associated with the gases where there's atoms or molecules motions, okay? We also often use a degrees of freedom argument, and it's mathematical conjecture without any real theoretical justification. Basically, degrees of freedom means how many directions can a molecule or something turn in, but the thing is, there has to be something that makes it turn in that direction. You don't automatically apply the degrees of freedom without a reason for that degree to exist as far as energy is concerned. And the other big issue, and probably even bigger, is gas molecules are treated like point particles. This was driven home to me by Dr. Ruggero Santilli, okay? But it's illogical because the fundamentals to statistical thermodynamics is everything's a point particle. Nothing's a point, okay? Every molecule has dimensionality to it. You can't just squeeze it into a point. Sure, it makes the math easier, but there are issues with it, okay? So traditional kinetic theory starts off with the gas molecule's momentum and treats the problem as if the gas molecules simply bounce off the walls, basically, right? There is no explanation as to how the gas molecules initially got their energy, right? It's as if they're born with energy. And walls and gases are treated like they're super balls and super walls, right? There's no consideration for the thermal radiation that resides in amongst the gas molecules. And we express all of the gas's energy in terms of the molecule's energy lens itself. This leads to the outrageous if you consider that there's no energy associated with the radiation and all the energies within the gas molecules itself, it leads to the outrageous claim that a vacuum has no energy. But vacuums have energy. If there's photons flying around in that vacuum, it has energy. Okay, just because that energy is small in comparison to the energy associated with molecules does not mean it doesn't exist. Okay, this becomes important. So let's talk about it. Okay, so I rewrote kinetic theory in 2017 and 2018, and they're in the journal Progress in Physics. Okay, and the reason the two journals or the two papers are written down below, it's 2017, 2018. The reason it got published is not that everyone appreciated what I had to say, but I clearly explained the heat capacities of gases without all those hideous exceptions that plague currently accepted kinetic theory. And these exceptions are often explained in terms of quantum terms, you know, or they're explained like things like because a gas molecule is so small, monatomic molecules are so small that their rotational energy is zero. But it's not, right? Or it's approximated to zero. It has rotational energy. It's just we got the math backwards, okay? So importantly, I wrote new equations and they're all superior fit for the heat capacity of gases. And that's why my papers were published. So if you care to look at it, there they are down below, right? Okay, and basically my kinetic theory considers that the system's six walls impose their kinetic energy through the vibration energy onto the colliding gas molecules. So now you understand how the gas molecules get energy, right? They hit the wall and the bigger, larger structured wall molecules impose their energetics onto the gas molecule. And this imposed energy is usually a function of kT over 2, right? And note that the energy of the gas is not mass dependent. I mean, if it was just collisional activities of gas molecules hitting each other, there'd be a mass dependence, right? But instead, there is no mass dependence because the wall is so big and so structured compared to the size of the gas molecules. The walls impose their energy onto the gases, and this is all a function of kT over 2. But at least now we understand how the gases get energy, right? The gas's vibrational energy also depends on the number of molecules in the atom, how many atoms are in the molecule, I'm sorry. So the vibration energy of a gas molecule depends on how many atoms it has inside, okay? And this is really about the absorption of the radiation and exchanges of energies with the walls, okay? But we can now understand why all gases have similar energy and it's not dependent on mass, right? And you'd think it's dependent on mass because kinetic theories, I mean, not kinetic theory, the kinetic energy is 1/2 mv squared. So there should be a mass term in there, but we start to understand why it doesn't exist. Okay, a requirement of kinetic theory, both mine and traditional, is that the gas is sufficiently dilute. This means that the majority of collisions are between the wall and the gas molecule. Okay, as soon as you get gas to gas molecule collisions dominating a system, okay, we can no longer use kinetic theory. And one must actually go and use the polytropic equation, which was invented for stars. It doesn't really have any proper theoretical basis, but it works, okay? But we're not talking about polytop. I'm just throwing that out there. Okay, so my new kinetic theory allows for inelastic collisions, okay? You can imagine if the walls are imposing their energy onto the gas molecules, then we understand why the gas molecules have the energy they have, and you don't need to have elastic collisions like you need in traditional kinetic theory. Okay, conservation of energy means photons result from an elastic collision. So when two atoms hit each other, doesn't matter what they are, it's an inelastic collision, and you get a photon as a result. Okay, an ensemble of such inelastic collisions will result in a spectrum of photons, and the most common spectrum that we see from this is black body radiation. Now, black body radiation is very vaguely written and stuff. We had Planck do all the math and all that stuff. It was all beautiful stuff, but it required an enclosure with, with walls and stuff like that. Well, things like our sun has black body radiation. There's no walls around it, and it's not enclosed, right? Okay, they argue that because the sun itself is so dense that it acts as an enclosure, but the argument is not needed. Okay, just realize that black body radiation is a result of collisions between molecules, and these collisions are inelastic, and therefore a spectrum of such collisions is black body radiation. You can understand as the temperature goes up, the velocity of the molecules colliding, or how much energy they collide with, goes up, and then the mean frequency of the black body radiation, or the peak frequency, goes up, right? So not all of a gas's energy should be associated with the gas molecule's kinematics, okay? I mean, at any instance, the total energy associated with the gas molecules is dominated by the kinematics of those gas molecules, the energetics associated with them. Therefore, as an approximation, all of a system's energy can be considered to be contained in the gas molecules. And this is why statistical thermodynamics remains valid, but it's an approximation, right? There's still energy associated with the photons in there, even though we can ignore it when doing the total energy of the system. Since the photon travels at the speed of light, while gas molecules travel at non-relativistic speeds, photons cannot be so easily ignored when it comes to heat transfer. And you can imagine, so the total energy of most gaseous systems can be approximated, as we do in statistical physics, by the kinematics of those gas molecules. But if you want to understand heat transfer, if photons are flying around there, they travel so fast that they've got to be considered as part of the heat transfer. Okay. And so this is just a picture that I drew, in one of my papers there for the journal Progress in Physics and stuff. But you can see that the gas molecules are flying around. Okay. And basically, even the diatomic gases shown on the right, you can see that there's photons leaving the gases. Okay, it's the two atoms in the diatomic molecule hit each other, and it also absorbs energy. Okay, but the point of this is the wall molecules themselves are imposing their energetics onto the gas. We start to understand what's happening. So there's 4 types of energy associated with the volume of gas, and 3 of them are kinematic. They're traditional, accepted, translational, rotational, vibrational. But you also have to have thermal energy. I'm sorry if I'm repeating myself, but thermal photons, primary infrared, but we've still got to test all this. They reside in free space. Another point of my kinetic theory does not go by degrees of freedom. And I realize that both the rotational and plus the translational energy are from the impact of the wall. So it's like a bat hitting a ball, right? It gives both translational and rotational energy onto that ball. So both translational and rotational energy are not 2 separate degrees of freedom, as is incorrectly traditionally thought. They're all part of one, right? And it's all part of 1 kT. Okay, and this is what differentiates my kinetic theory from the other one, and this is why my kinetic theory actually fits empirical findings so much better than traditional kinetic theory. Okay, it's not accepted because we're all indoctrinated with the traditional, but that's where it goes. Okay, thermal equilibrium, therefore, no longer involves just the exchange of kinematic energy. It also involves the absorption and the emission of photons, generally a black body spectrum. If photons are emitted due to collisions, then they must also be absorbed by matter. And this is both condensed matter and gases. Such photons can be thought of as thermal photons. Now, no one ever talks about thermal photons but me and my dog. But the point is, thermal photons pass their momentum onto the atoms inside molecules, and that's how they're absorbed. Okay. Now, this was inadvertently shown by Thomas Almendinger using directional light. Now, I read Thomas's paper because he was talking about a new way of thinking about global warming and stuff like that. And I sort of missed this, but at one point there, I got in an argument with somebody, and I reread Thomas's paper, and I realized that even though he wasn't trying to do it, and he didn't realize he did it, he proved that photons get absorbed by gas molecules. Okay, and his paper is Thermal Behavior of Gases Under the Influence of Infrared Radiation. It was published in 2016. He's also published other papers. He's also, a dissident scientist in some ways, but he proved without trying that photons pass their momentum on. So I recommend you read that paper, but you might want to also read my paper, New Thermodynamics, Wave Particle Duality and Radiative Heat Transfer. That's in the Hydraulic Journal. Okay, and basically I talk about what Thomas did and how he did it and all that stuff. Okay, but basically he showed the missing idea that a photon not only acts as a wave, okay, it acts as a wave and it can interact with a molecule's electron distribution, especially if it's lopsided, but it also acts as a particle where it can hit the atom and it can pass momentum onto the atom. It's really no different if you think about it than putting one of those big sails in space and using the sun's rays or a beam of rays to power that device so it travels through space with increasing velocity as more photons hit it, right? It's just photons passing momentum onto a particle, okay? So this happens at both the atomic scale and the large scale, okay? So the maintenance of thermal equilibrium involves a combination of reflection of photons by surfaces. Right? We like to put aluminum surfaces in a lot of our experiments and stuff, and that reflects the energy of the photons, so they just bounce around. But the photons are also absorbed, okay? Thermal photons are absorbed. They pass their momentum into the walls, right? And they become phonons in the walls. And then the emission of these photons, emissions of these phonons, they turn into photons as the wall emits them, right? And this is due to both inter and intramolecular collisions, right? And we also have this exchange of kinematic energy during collision. So we've sort of changed things, okay? Now, I want to point something out. The recycling of energy back into a system by its walls gives the illusion of elastic collision. So when you're working with a system, okay, not only are the gas molecules the dominant energy in that gaseous closed system, such as an experimental system, but we've got the recycling of the photons back into the system. I mean, this includes both reflection. Reflection is the recycling of the photons back in the system, as well as the absorption and the emission of photons by the walls, right? So when you're doing an experimental system, you have the illusion of elastic collisions, and the system can be approximated by statistical thermodynamics, and you can understand where the problem is, okay? But when you have an open system, you can envision that collision-induced photons can be lost as they disappear to one's horizon, right? The sun itself, we get a whole bunch of them, they heat up and light up the earth, right? And, so you can't just go thinking in terms of closed system physics and go into open system, because you no longer have the illusion of elastic collisions. Photons are disappearing out of your system as they go into one's horizons, right? So although we can approximate the total gas energy purely in terms of the gas's kinematics, especially for closed systems and experimental systems, basically it loses its validity. Those approximations lose their validity as more and more photons disappear from the system, right, in open systems. So the more photons that escape any open system, the less valid any traditional approximation is. right? And I gotta emphasize this. We're sufficiently dilute closed gaseous systems can be approximated by our indoctrinated laws of physics, such as statistical physics, Maxwell's velocities, distributions. The ideal gas law falls into this. Avogadro's hypothesis falls into this. Accepted kinetic theory all falls into this, right? And so you approximate it as elastic collisions. The problem is, again, I got to repeat, open systems are not closed systems. Such approximations do not apply to open systems. And this is going to be dangerous for some people because we get it ingrained in our head that, you know, the ideal law, gas law, and then we apply it to, you know, to our atmospheric physics. It doesn't really apply. It's a rough approximation, right? So since elastic collisions incorrectly consider that all of gas's energy is held in its kinematics, this explains why many claim a vacuum has no energy. I think I said this earlier, but it's still nuts. If there are photons in a vacuum, it has energy. I am sorry, you know. So we also can conclude that experiments are often founded upon unrealistic expectations, considerations, and what have you, right? You can't take a closed system of gas and apply it to open system physics. You know, it's going to be a rough approximation. How rough? Well, it's going to vary by a case-to-case situation, okay? So for emphasis, continued. Closed systems, orthogonal walls, they pump that energy into the gas, right? So then you have things like the ideal gas law, you have everything, right? But the illusion of elastic molecular collisions haven't, well, it's really emboldened those who adhere to probability-based statistical thermodynamics, right? Everyone's, yeah, this all works, it all matches. Well, that is all limited to closed systems, right? Elastic collisions, I mean, the point is, another point here is you got to realize elastic collisions simplify the math. I know Boltzmann's math pushes me to my limits, and I'm not even sure if I'd want to deal with it today. I mean, when I was in university and stuff. But the point is that it's a simplified math. Can you imagine an open system where you got photons being absorbed by molecules and all this stuff happening, and then photons being emitted by molecules, you know, gas molecules in the atmosphere, what have you? It becomes a horrendous task, right? So you can imagine how much Boltzmann's math simplifies the situation, right? And it is very helpful for closed system mechanical aspects. But most theories in physics are based upon elastic collisions and this sort of ideology. So most of physics will need a rethink. I mean, we were even talking, someone mentioned the Navier-Stokes equation on my last video. Once more, that's based on elastic collisions. It falls into this problem where it's going to falter as soon as you start getting into inelastic collisions, which is reality. Okay, this all has meanings. I mean, implications beyond what I'm talking about. Consider Boltzmann's constant. Okay, it is accepted as a proportionality constant between entropy and the number of states. Well, I've thrown out entropy, but let's still look at it, right? S equals K ln, you know, number of states. Okay, omega, you know, number of states. Well, it's a proportionality constant to a mathematical constants, which is entropy. Okay, but we can rewrite the ideal gas law as K equals PV NT, and then differentiate and treat the process as isobaric, and we get the simpler understanding that K is the amount of lost work per molecule per temperature change that a gas can do. And this is really a closed system of gas. I should say that it's not an open gas. So you got a gas in a closed system. K defines how much work it could do per molecule per temperature change, right? And this is going to be a shocker to some people. But if you take a look at this, you can understand PDV is now volume change, and that was related to randomness. You can see how people made the mistake of associating randomness with entropy and, you know, Boltzmann's constant stuff. But it was wrong. The simpler solution is number 2. And this also means that Boltzmann's constant is not a universal constant. It is a constant here on Earth because the amount of work it can do is going to be related to the gravitation of the Earth, right? So there's going to be some trickiness here. I don't say I've got everything figured out, but you start to see where I'm coming from. Okay, so one with a vested interest in traditional dogma should realize that equation 2 is structured around isobaric volume increase. It is similar to the accepted concepts of entropy. I just said that, I'm repeating myself again. I apologize. The association of the increase in possible number of energy states to a system's volume increase gains clarity. We understand now why the two maths jive, but it does not make it right. Okay, and I talk about this in my most recent paper, New Thermodynamics, the second law buried by illusions. It should be out in the Hydronic Journal. I mentioned it earlier. It should be out real soon if it's not out yet. I get that one. Okay, so do approximations such as Avogadro's hypothesis, ideal gas law, statistical thermodynamics, Maxwell's velocity, etc., even apply to open systems. I mentioned this before. It's an approximation. It will need to be evaluated on a case-by-case basis, but we have to start thinking in these terms, you know? And you kind of remember, open systems traditionally lack any explanation how do gas molecules actually obtain their thermal energy in the first place, right? So, I mean, we assume that the gas molecules all had energy to start and all this stuff. No, they have structured energy because they bounce off things, okay? But we also start to realize now that, you know, diatomic gases such as oxide nitrogen in our atmosphere can absorb thermal photons. So they get the energy there. They have a vibrational energy. They exchange that during collision. So it becomes a bit of a mess, but you can understand, you can actually start to understand why the mess exists, right? Many realms of science, atmospheric physics, namely, and cosmology will need close scrutiny before one begins the overhaul, you know? And I also talk about this a bit in one of my papers that just came out earlier this year. Even though it says 2021, it came out, I don't know, earlier in 2022. But it's New Thermodynamics, questioning temperature in open systems and in atmospheric physics. I am sorry, but once we start questioning everything like Avogadro's hypothesis, ideal gas law stuff, you start to realize that you've got to question what temperature means. And temperature is going to have a different meaning in an open system than it does in a closed system. And this is going to also be really difficult, but I mean, I could talk about that for hours, so we might as well just leave it. If you want to read this paper, please do. I'd appreciate that. Okay. So Boltzmann's statistical thermodynamics and Maxwell's molecular chaos hypothesis are brilliant. Yeah, they're brilliant mathematical deductions, but they require these assumptions. And I'm repeating myself again, but it has to be driven home. They require colliding molecules, atoms, to be treated as point particles. They're not. They have dimensionality. Okay, the velocity of each such colliding particles are not correlated. Well, they would be correlated if you treated, you know, just them hitting each other and having masses and stuff like that, right? But right now, the way it's structured, because we do it based on gases and stuff in a closed system where the walls impose their energy on it, that becomes a valid statement. It's going to lose its validity when you go to open systems. Velocities are independent of both their position and origins. Well, once more, that is a statement that applies more to closed experimental systems than it does to reality, okay? And point particle collisions are elastic. Well, they're not. They're inelastic, right? So again, we can understand why statistical thermodynamics falters, whether you take Boltzmann's or Maxwell's version. Okay, but one of the beauties of their math is it allows the probability of a pair of colliding particles to be calculated considering each particle separately. This allows a two-particle distribution function to be reduced to the product of one-particle distributions, right? This simplifies the math. It makes it doable. Can you imagine an open system and you to realize what I'm talking about? Well, this doesn't apply. I don't know what you're going to do. I really don't. I'm not that great at math, and it's going to take a whiz much smarter than most humans, very smart for a human and much smarter than the rest of us, right? This allows one to ignore the probability of finding one particle with a velocity and another one with another velocity in an infinitesimal region. Thus, the particle's energy can be computed because they obey new random distribution, right? But we understand now that this is limited to closed experimental systems and sufficiently dilute ones to be exact, right? So we have other issues. You got the truncated Hamiltonian and Lagrangian. I don't know if you know what I mean by truncated, but it basically, when you Hamiltonian and Lagrangian, assume everything is elastic. You take off one of the terms, and you just left with, you know, the kinetic and potential energy associated with those molecules. But we can no longer use the Hamiltonian or Lagrangian with impunity, especially when you're dealing with open systems, right? And so they too are approximations that simplify the math. But accepting that statistical thermodynamics is an approximation, often rough, for closed systems means that one has to question to what degree all this stuff can be applied to our universe. It also returns us to the EPR argument, you know, Einstein, Podolsky, and Rosen concerning quantum physics, right? And their concern was, does probabilities define everything? No, probability math, it's a descriptor. It's a descriptor that works good for closed systems and sufficiently dilute gases. It's not something that you can go and say, oh, the whole universe works on this probability. It doesn't, right? We have to rewrite the way we do probabilities. I also, when you're doing thermal energy exchange, you know, between molecules, and the way we write those probabilities is dangerous. And I have rewritten the probabilities in certain terms, but I still need help. I'm not perfect. I'm far from getting it all right. So anyways, that's the way it is. Okay, where am I on that page? So I'm going here. Okay, now this brings us to climate change. Dennis started talking about it earlier and stuff, but all polyatomic gases absorb a photon's energy, and this includes homonuclear oxygen and nitrogen. Okay, we traditionally thought of it as being opaque or transparent to photons, but it's not. And this was shown by Thomas Almendinger. I mean, I talked about him earlier. He inadvertently did an experiment trying to show one thing, and he did show it. But the point is, he also showed that all molecules absorb infrared energy. And he shone a directional infrared light onto a bunch of photons, and he measured the temperature increases and stuff. And traditional theory couldn't explain it. And so his paper hasn't been well accepted. But when I read it for the second or third time, it just hit me like a wall of bricks of what was happening there. And so that's why I wrote my paper in Hydronic Journal that I mentioned earlier. Okay, so heat transfer primarily involves the absorption of thermal photons, photons acting as particles. Okay, secondary is photons acting as waves. I've repeated this before, and this is you know, acting with the, you know, lopsided charge distributions. It's photons acting as waves that we see in infrared spectrometry. Okay, and I'm going to explain to you why that happened in a few minutes here. But anyways, our whole atmosphere is a thermal blanket. Every molecule absorbs thermal energy. It's not just our greenhouse gases. So climate change based on greenhouse gases is a very dangerous solution. It really started with John Tyndall, a very famous Irishman physicist, and his mistakes and a litany of mistakes that drives me nuts. But anyways, we're just going over the generalities at this point. But climate change is still anthropogenic. Okay, this means it's caused by man. The better explanation becomes our total energy use all degrades into heat at some point, and this is the root cause of the man's contribution to global warming. The problem is, until we rewrite atmospheric physics, one must accept that there are problems and that we've got to, you know, and that I don't have all the answers yet, but rewriting atmospheric physics is going to take a lot of thought, a lot of input from a lot of very smart people, and I don't even know if they're going to get it right. It's just going to be too complicated. But one must accept that anthropogenic climate change is real. I mean, I just saw it in my place. I mean, this house, my family's lived here since 1952. I mean, I got kicked out after high school, but I took over. Anyways, the point is, I lost 20 some odd trees the other month there, blown down by 130-kilometer-hour winds. We've never seen that here, right? It's climate change is real. It's happening to everybody, okay? So we must realize that all of our energy use ends up in our atmosphere. Since we're not quite smart enough to figure all this out yet, it becomes prudent to realize that in order to prevent climate change, we must limit our energy use, okay? Or we must only use energy that is extracted from the atmosphere. So you can imagine, if I'm extracting wind energy out of the atmosphere, I'm extracting kinetic energy out of the atmosphere. I can now use that energy and I return it to the atmosphere without causing problems, okay? This is net zero energy use. If you burn oil, you burn nuclear fuel, you burn anything, you're adding energy to the atmosphere. Okay, we're just going to kill ourselves. You know, the only thing that saves me is I don't know how many kids, right? But part of the blunder is due to infrared spectrometry. I talked about this. What we do when we do infrared spectrometry is one of the first steps we do is we measure the blackbody radiation inside the spectrometer, right? And then we subtract it from the output spectrum. But when you realize that blackbody radiation is the radiation that defines the thermal energy within the system, it's created by inelastic collisions of molecules. It's absorbed, its momentum is absorbed by the molecules and all that stuff. Then you start realizing that the removal of a blackbody radiation spectrum from the spectrometer is, from the spectrometer's output, is a removal of spectrometer's thermal signature. It's also the removal of the gas's thermal signature. Okay, so a spectrometer's output now becomes based on photons acting as waves, not particles, right? The black body radiation that we see within the spectrometer that we move from it is photons acting as particles, passing momentum onto matter, right? The output spectrums that we see and we jump all over and we say, well, this is why greenhouse gases do this and do that. That is just, photons acting as waves. It's not really, it's secondary to photons acting as thermal photons or as particles, okay? I talk about this in many papers, and my most recent paper is this new thermodynamics, wave particle duality and radiative heat transfer. It's in the Hydronic Journal. It's, volume 44, and it was published just late last year, okay? So where am I? Okay, just so you know, I'm a bit of an oddball. I mean, you can't explain it any other way. I mean, I rewrote nucleation theory, and then I realized that there's something wrong with thermodynamics. So I've written a book. I've never published it on, nucleation theory. I got to revise it again. But anyways, then I said, oh, there's something wrong with thermodynamics. Let me just buzz through it, and I wound up writing the whole science. And so I've rewritten kinetic theory, free energies, latent heat, inelastic collisions. I got challenges to the second law, Boltzmann statistics. I sort of I've dabbled in places that don't belong, but it's the only way I can make sense out of all this. Experimental proofs for Boltzmann stats is limited to sufficiently dilute gases. Due to 8 and 9, stats do not apply to open systems. Due to 8 through 10s, Boltzmann stats remain an approximation to what is witnessed in closed systems. Things like kinetic energy, ideal gas law are all limited to closed systems, sufficiently dilute ones, such as those used in experiments. Entropy is a mathematical contrivance. We've talked about this in the last two presentations. Open systems cannot be deduced from traditional theory. Atmospheric physics must be rewritten. Ditto for cosmology. I mean, if you think about it, cosmic background radiation can now be explained, as 2.7 degree radiation due to collisions of matter in deep cold space, right? 2.7 degrees. So we can understand why black body radiation exists. I wrote about that in a paper. It didn't go over very well, but anyways, it's out there somewhere. I'm sorry. Global warming must be rewritten. I just talked about that. The meaning of Boltzmann's constant changes. I've also rewritten why tensile layers exist and what they are, and I've rewritten capillary reaction. I don't know if you guys want to see it, but here's a partial list. I'll go through it quickly with some of my papers and give you a chance to nail me with questions. Anyways, I'm somewhere just under 40 papers. I don't know if you want to see them all, or we can put them up somewhere else. Okay, guys, thank you for your time. Questions? Did I talk too fast?
You say that global warming is using energy that's not from the atmosphere, and it accumulates over time.
It accumulates over time, but the addition of global, I mean, we draw these graphs and stuff like that showing, oh, CO2's gone up and temperature's gone up on the planet and stuff. Well, you might as well draw a graph saying, ladies in the workforce have increased over the last few years, the temperatures go up, and blame it on women. It makes no sense, right? Basically, what I am saying,
that CO2 is the problem. Do you believe that?
No, I don't, because CO2 is no different than any other triatomic gas. It absorbs thermal energy, as I talked about. It absorbs the photon's momentum. The problem is in infrared spectrometry, CO2 has a lopsided charge distribution, so it also absorbs photons as waves. And you see that in infrared spectrometry. But as I was stating, in all gases absorb and radiate black body radiation. Okay, and so infrared spectrometry, the energy associated with that is minute compared to the energy that the photons pass on to each other. So all triatomic gases absorb heat the same way. That's why all triatomic gases have similar heat capacities. So all diatomic gases have similar heat capacities. If it was purely on the charge distribution of each gas molecule, then you'd see the heat capacity being really having big variances between each molecule. It doesn't matter. Each triatomic molecule will have a completely different heat capacity depending on how much heat it absorbs. It doesn't. It has the same heat capacity whether it's got a lopsided discharge distribution or not, right? It just depends on its triatomic. Okay, and so you can understand how we blew it. So carbon dioxide is no different than any other molecule. The two molecules that absorb the most heat in our atmosphere, oxygen and nitrogen, because they're diatomic, so they can absorb energy. But the point is, there's so much of it. It's 99%